All right, those are the steps. I think once I do an example, you'll see what I mean, all right? So first example, I want us to sketch the function f of x is log base 2 of x. So you have to look at it first. Is that a logarithmic function? Yes, that's a log function. And what is the base of this log function? 2. So my first step is just to make sure that I've got a log function, and I'm even going to put here my base is 2. All right? Just kind of identifying what my base is. The next step is to make a t-table for a to the x. What? That means make a t-table for a to the x. What's a to the x here for me? 2 to the x. So I'm going to put x here and 2 to the x. Do y'all recognize what 2 to the x is? What is 2 to the x? What type of function is 2 to the x? That's an exponential function. Why the hell am I making a t-table for the exponential function? Because the log is the reverse of it, right? So if I know all the points that belong to the exponential function, if I reverse them, then that should be the log function. Let me put it down. Now, what did we say were the numbers we like to plug in here? So we're going to always use those same numbers. And then we already know we got like 1/8, 1/4, 1/2, 1, 2, 4, and 8, right? The third step and the final step is to switch the x and y coordinates. So think about this. The exponential function takes this number, spits out this number, right? Our log function does the reverse. It takes 1/8 and it spits out -3. It takes 1/4 and it spits out -2. It takes 1/2 and spits out -1. Takes 1, spits out 0. Takes 2, spits out 1. Takes 4, spits out 2, and takes 8 and spits out 3. So do you see what I've done is just taken this table and flipped them all over? Reversed them, switched the x and y coordinates? Any questions? I'm going to plot all these points. 1, 2, 3, 4, 5, 6, 7 points. I'm going to plot them. When I plot them, I should have a pretty good idea what this looks like. Tell me a little bit about my picture. What's the biggest x value I get? Biggest x coordinate? 8. Smallest x coordinate? I don't have any negative numbers, do I? Do y'all notice none of my x's are negative? None of my x's are negative. Well, where do these x's come from where? These? Are these ever negative? No. These will never be negative. So when I draw my x-axis for my log function, I only need to draw it to the right, really, because to the left, my picture is not going to even exist. How about my y values? What's the biggest y value I have? 3, the smallest? -3. So I just need to be able to go up 3 and down 3. Got it? So let's plot some points. And I'm not going to do these fractions first. I'm going to do the nice numbers first. 1, 0 means I go to the right one and I don't go up or down, right? So to the right 1, 2, 3, 4, 5, 6, 7, 8 was the furthest we need to go out, right? So I'm going to put 8 out here. And so I'm plotting now the point 1, 0, which puts me here. This is part of my graph, right? The next point that I have, I'm avoiding the fractions, 2, 1. So to the right, 2 up 1. Agreed? The next one, 4, 2, right? So now 1, 2, 3, 4 up 2. That puts me here. And then the last one of these nice ones is 8, 3. So out 8, up 3. Y'all seen this or no? Everyone see it? All right, let's try some of these fractions. 1/2 negative 1. That means to the right 1/2 down 1. To the right 1/2 down 1. That puts me here, doesn't it? What about the next one? To the right 1/4 down 2. That's going to get harder to put, you know, if this is halfway, 1/4 is half of that, so something like this. What about the next one? 1/8 down 3. So 1/8 is even less, and then down 3, something like this. What do you think is happening there? Yeah, didn't we deal with something like this before? Where it dove down but never really touched. We called this thing a asymptote. Yeah, a little more. Vertical asymptote. Didn't we call it a vertical asymptote? That's exactly what's happening here. Okay, so if I draw this, it's kind of like back in kindergarten here. I'm going to connect the dots. It's going like this, all right? And then over here, the y-axis is acting like a barrier, okay? And I'll put a dotted line here. That's a vertical asymptote, and it dives down forever. Just keeps going down. The closer you get to 0, the further it dips down. Right? Because I can keep on getting closer and closer to 0 without getting there. If you're not convinced of that, go back to this table right here and take something like, I don't know, -10 and plug it into this. And you're going to get a tiny little number. And that would mean you move to the right just a little bit, and then you go down 10. And you can keep doing that forever. You're never going to run out of numbers. So it dives down. I'm going to put VA here for vertical asymptote. Now, does it have a horizontal asymptote? What do you think? It actually does not, because it's going to keep growing, okay? The thing is, it's not going to grow as fast as an exponential function grows. As you go to the right, it will continue to go up and up and up, just kind of slow, all right? So that's what this logarithm looks like. What do y'all think? So what do y'all think about the graphing of it? Is it pretty straightforward? So if I change this, right, and I ask you to graph log base 4 of x, then you're going to change this to a 4. You're going to change this to a 4. Then you got to redo all this, right? Figure out what those are, flip them, and then plot them.
So before to the negative 3.
Yeah, this would be 4 to the -3, which would be the same as 1 over 4 cubed, which is going to be 1/64. The next one will be 1/16, and so on and so forth. Yes?
This is only for exponential functions, correct? Like versus the log?
The log is only for undoing the exponential functions, yes. How are y'all doing? It's all right? All right. Feels like a Monday? So in general, if someone gives you a function f of x is log base a of x, it's going to look like one of two things. Do you remember with exponential functions we either had exponential growth or exponential decay? I drew it on the board. With exponentials, we either had this or we had this, right? There's one or the other with exponentials. Same thing with logs. We have two different possibilities. It's going to look like this. If a is greater than 0, and this will always be a vertical asymptote right here. Or it's going to look like this. kind of like flipped over. If a is less than 1, oh, oops, sorry, that's a mistake. I meant to put 1 here. You might remember this from the exponential functions. We have exponential growth if a was bigger than 1. We had exponential decay if a was less than 1 but greater than 0. So you can go back and look in your notes. Exponential growth was when a is bigger than 1. If a is bigger than 1, then the log function, its inverse looks like this. And if we have exponential decay, the inverse function looks like this. All right? All right. I wish I could say that, well, that's it. But there's something we have to look at. There's a calculator, a key on your calculator that we can use. And we need to get familiar with that. But before I can get familiar with it, I want to ask you a few questions to kind of warm up to this. What's log base 10 of 100? 2? I thought it was 10, no? If I think that's 10, what mistake am I making? I'm thinking 10 times 10 is 100. That's not what this is asking, right? This is saying 10 to what power is 100? So 10 squared. So 2. All right. What's log base 10 of 1,000? 3. 10 cubed is 1,000. Yeah? What is log base 10 of 7? Uh-oh. What is it?
0.845.
What? How'd you do that?
I learned this in high school.
But you used that, right?
Yeah.
Okay, so what did you type there?
Log 7 divided by log 10.
You did, wait, what log key? Let me see what key you're using. Which one?
This one right there.
Okay, yeah. So I was hoping that someone would do this. You found a key on your calculator that said log. Anyone else have a key on their calculator that says log on it? Right? What's wrong? Don't panic. What is that key? What's missing on that key? What piece of information is it not giving you? What base it is, right? That doesn't tell you all of these logarithms, every single one I've given you, right? We've had to have a base in order to figure out the answer to the question, right? This doesn't give you a base. It's base 10. Now, do you remember this? If I write this, it's understood that this means the square root. Do y'all ever remember someone telling you that means square root out there? There's a 2 out there, but we don't write it. As opposed to something like this. If I want cube root, I have to put the 3 out there to let you know it's a cube root. But if I don't put it out there, it's understood to be a 2. Same thing with this log. If you see log without anything written below it, it's understood to be a 10. In other words, another way I could have written this problem would be this. log 7. So you actually could have just typed in log 7 and you would have been done. So try and find your log key. Do you have a log key on there? Yes, it is. Let me see, where is it? Yeah. Try and use your calculator to do log 7 and tell me what you get. 0.845, approximately 0.845.
How do you type in the calculator when you do log?
Well, type in log, right? And what does it give you after that?
Gives me a parenthesis.
Okay, so now you're just going to put 7 and then close a parenthesis and hit enter.
Oh.
Got it? Okay, this is very important that you understand what's going on here, all right? It's a subtle thing, but if I write now log 100, do not use your calculator, log 100, what's the answer? 2. This is the same question as this one, isn't it? If you do not write the base, it's understood to be 10. Got that? And the reason why we do that is because the base 10 log is a very important log. Why do you think base 10 is so important in our number system? Base 10.
So everything's based off of base 10?
All of our number system is base 10, right? You all know what that means? Base 10? Here's what base 10 means. I'm just going to explain it to you. In base 10, to say we have a base 10 number system means that all of our numbers are based on 10 digits. These are them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the 10 digits that we have in our number system. There's no 11th digit or 12th digit. Those are them, right? Now, if you're working with computers, it's base 2, and the only digits they use are zeros and ones. That's a base 2 number system. All right? So base 10 is super important to us because that's what we use, base 10. And where do you think we got base 10 from? Why not use base 8? I mean, why is it that we had 10 digits? Why isn't that we had just 7 digits? Because that would be a base 8 number system. 1, 2, 3, 4, 5, 6, 7, 8. 8 digits. Why do you think we have base 10 and not base 7 or base 8 or base 5 or base 30? Anyone have an idea of why we would?
Think of any more strange symbols to represent numbers?
But I'm saying, what about why 10 though? No, because I could have come up with other symbols. I mean, we could have, right? We could have kept going, like 8, 9. I like your idea. Your idea is that we couldn't come up with any more strange symbols because these to us are like the only symbols. But I mean, why couldn't I have something like that? And that would be my next digit.
Kind of looks like.
Right? Why not? I have no idea why we would have base 10. No idea. No idea?
Oh, hands.
What about your hands?
Or digits on fingers.
We have 10 fingers. It's that simple. It's that simple. That's why we're base 10. If we had 8 fingers, we would be using a base 8 number system. That's why we do it. So for us, 10 is like this great number because of this, right? Now, I guess we could have gone base 20 if we want to start counting on our toes also, but we always just used our hands. Does that make sense to you? I mean, that's actually pretty, I don't know, intuitive. It's our hands. It's the number of fingers we have. So base 10, because it's so important, when we have log base 10, we just write log. And it happens so much in our number system, in our calculations, that it's just easier to write log. And there's another special one. So log base 10 is special, and the other special one is this one, log base E. So what if I say log base E of 7? What does this mean? In words, what am I saying? E raised to what power is 7, right? E to what power is 7? No one's going to get that for me, okay? No one's going to mentally be able to just say, oh yeah, e to the blah, 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 and give me the answer without a calculator. No one's going to be able to. But maybe there's a log base E button on your calculator. There is, but they've hidden it from you. It's this one. It's this button. ln means log base E. That's what it means. So if you ln should be above the E. Oh, it is, it's the, yeah. It looks like IN, right? It looks like, it's not IN, it's LN. It's lowercase l, lowercase n. And it's, I didn't talk about this, LN? It's French. You know how the French do things backwards? Like, it's logarithm naturel. The natural logarithm. Okay, so do you remember me talking about the natural exponential function? I said there was this very special number that only that number worked, and I said it was e. So we call it the natural exponential function. This one right here is called the natural log function. So to do this one on your calculator, go ahead and do it. Do natural log 7.
1.945.
Say again? 9.5, close enough, approximately, all right? That means if you take e and you raise it to about 1.95, you should get about 7. So that's good. All of our calculators have built into them logs which allow us to handle all base 10 logs and all base e logs. Isn't that nice?
It's so nice.
Yeah, it's nice. We can do that. Until someone comes along and gives you this problem. And they say, what is log base 5 of 31? Is it Helen? You're Helen. Helen's going to crank the answer out here in a second. What do you got, Helen?
2.13.
Say it again.
2.13.
2.13. Helen bought the silver edition special calculator that nobody else has access to. So she has very special keys on hers. No. You're using a formula, right, Helen?
Yeah.
There's a formula because look, what we realize, mathematicians, is that look, it would be nice if we could like solve any log, right? Because imagine you could have any base here, right? And if you needed a key for each base, then you would run out of keys, right, on your calculator. So we actually came up with a formula that allows you to solve any log. And here's the formula. This is called the change of base formula. And it says this: if you have a log, and it does not matter what the base is, we'll call it a, and you're trying to plug some number in here like x. So in this particular problem, a is 5, x is 31. Okay? That this is just equal to the natural log of x divided by the natural log of a. Or if you don't like that formula, you can do the log key instead, and it's going to give you the same answer. Everybody's calculator has the natural log key on it. Everyone does. Not every calculator has a log key. Like my calculator, this is a TI-89, oops, which is the fanciest calculator, well, before they came out with the colored ones. This is like one of the fanciest calculators you can get. It does not have an LOG key. It knows that somebody using this calculator should know that this formula exists and that you don't need the LOG key. So that's why it's not there. Okay? Understand? So that this is a formula you can use. You use this, right? Okay, which is fine, but if you don't have a log key on your calculator, you can use this one. So I want everyone to try this. Please keep in mind, you're going to have to do two computations. The natural log of something divided by the natural log of something else. So for this one right here, to get this answer that Helen gave us of 2.13, we need to type into our calculators natural log of what? 31 divided by natural log of 5. Everyone do that on your calculators. Make sure you get approximately 2.31.
Yes.
What do you get? 2.13. Everyone get that? Approximately 2.13. Anybody not get that? So if you don't have your calculator, it's on you to go home and make sure you can get those answers. So in theory now, we can solve any log. In theory, right? All right, so try this one. What's log base 4 of negative 2? Make sure you use your negative key, not your subtraction key. What do you get?
Domain error.
Domain error. It actually says domain error?
Yeah.
What does yours say? Did you try it? And what do these say? Anything? Just error? Yeah, there's a problem here. Domain error, there's a problem. What did we say all log functions look like? If we graph them, they're either going to look like this, right? Or they're going to look like this. Remember that? We had a vertical asymptote here. What we're asking is, hey, what happens if you plug negative 2 into a log? So that means negative 2 is over here, right? Negative 2. And that's not happening, right? There's no graph over here. This function doesn't exist. And we didn't talk a lot in this class about domains and ranges, but basically this is an invalid input. You cannot put a negative number into a log. You're not allowed to. Try and put 0. Just on your calculator, try log of 0. Is that going to work? We have vertical asymptote at 0, right? You should not be able to plug 0 in. You should get the domain error again. So we can almost solve any log. As long as it's a legitimate log, we can do it.
How would you know when to use the equation you gave us? Like, how can you tell for those sort of
For the change of base, how do we know to do this? If the base is not 10 or the base is not e, you would use that. All right, so what I'm going to do now is I'm going to give you some problems to work on for homework. I'm going to just write them up here on the board for you. All right, so first problem is going to be multiple pieces. I want you to try and do these without your calculator. Okay, I want try and do all of those by hand without any calculator. Second one, sketch. Okay, I'm going to give you two of these. I want you to sketch two functions. F of x is log base 3 of x. And then the other one, f of x, is log base 1/3 x. So the base of this one is 3. The base of this one is 1/3. And then the next ones, what I want you to do is use your calculator for these. This is just an exercise, just to make sure you're using your calculator properly. So I want you to do log base 8 of 21, log 42, natural log of 1/2, log base 6 of 1/2.
Is that 1/2 powering the 6 or just 1/2?
Where here?
Yeah.
It's this is the base. It's down here. It just lets you know what the base is. This is the x being plugged in.
Okay.
That's the x being plugged in. Everyone understand? Try and get that done. And then we'll meet on Thursday and
Have some fun.
we'll see where we are in the syllabus. And anybody else need to turn in your take-home quiz? Everybody have a great day.
You too, sir.